All right, guys, so the second and the final part of 4.4 that we're looking into is minimizing average cost. So our goal for today is one, to find what minimizing average cost really actually is, and then let's use it in some application as to how can we find a production level in terms of where is the minimal average cost to produce this product, okay? So what is minimizing average cost, or what is the minimal average cost? This is happening where the production level at which the average cost is smallest. All right, so the average cost is absolutely smallest. And this is going to happen when the average cost equals the marginal cost. This happens when, okay, we find our average cost, the production level where the average cost equals the marginal cost. So let's think about that for a sec. What does the average cost and the marginal cost think about? We know that cost is represented by C of X for some particular product X, right? So if I want to find out what the average is, well, think about it. What can you use to find the average of that cost? Hopefully you can kind of take into account, well, this is just like back from Algebra 1 where we talked about how do you find the average of anything? Well, you take the total number and divide it by the total number of units specifically. So if I want to find the average cost, I would take the cost and divide it by however many units that I am dealing with particularly. And then this production level where we have the minimal average cost happens when the average cost equals marginal cost. So remember what marginal cost really was. The marginal cost was just that first derivative of cost. So really, when I'm trying to minimize average cost, my goal is to find where the average cost is equal to my marginal cost, right? Because remember, marginal is that first derivative. It finds kind of the difference between our production and our revenue and our cost. So let's take a look here at an example as to how can we really find a production value that is the average cost, the smallest average cost to produce this item. So we got an example here for you guys. Let's kind of keep that there as well with our goal. So suppose we have a function x cubed minus 6x squared plus 15x. And once again, x is in thousands of units. Is there a production level that minimizes the average cost, the total cost divided by the number of units? If so, where is it? So I need to know a spot in which C of x over x is equal to C prime of x. That is what my kind of goal is when it is all said and done. So let's first and foremost find out what C prime of x is going to be. So C prime of x is the derivative of our function. So in this case it would be 3x squared minus 12x plus 15. I also need to know what C of x over x is. So let's divide C of x over x. And in this case, we're going to get x cubed minus 6x squared plus 15x all divided by x. Well, one x will cancel there, one x will cancel there, x will cancel there. And so you are left with x squared minus 6x plus 15. So I want to know where these two functions are going to be equal to each other. What value for x, what production level am I going to find these two functions equal to each other? So let's set them equal to each other and see what happens. So I have 3x squared minus 12x plus 15 is equal to x squared minus 6x plus 15. Set them equal to each other, combine your like terms. So I get 2x squared plus, oops, I'm sorry, that is not plus, it becomes minus still. minus 6x. And then when I subtract 15, that cancels out. So this is set equal to 0 now. So now I'm going to find those values for x that do make this function equal to 0. Well, let's go ahead and just factor out. There's a 2x in both of them, so let's factor out a 2x. So we get x minus 3 times 2x is equal to 0. So our two spots and with this function will equal 0 is when x equals 0 and when x equals 3. So these are the two spots, all right? Well, x has to be greater than 0, right? Because you have to specifically have some kind of product, right? So x cannot be 0 in this case. So we know x must be greater than 0. So really, the production level is going to be happening at x equals 3 to minimize the average cost, okay? And so this is going to kind of help us, a little bit as to where we could possibly find what's going to happen. And so let's think about this for a second, though. The fact that x equals 3 does give us a possibility. Also think about what it could tell us. It could possibly just be a local min and not necessarily the absolute min. So we can kind of use the second derivative test to help us find what the absolute min is going to be. Okay, so let's take take a stab into what the second derivative is. So of my function c of x over x, this is our original c of x over x. This function here was x squared minus 6x plus 15, okay? So here's our original average cost. So remember, we have to make sure that this is going to be an absolute minimum, okay? And really what we're just trying to show is that x is going to be greater than 0 or positive when we take that second derivative. So derivative 1, c prime of x over x, I guess should be kind of, this whole thing should be primed, really. Let's erase this one here. So prime is going to be 2x minus 6, and then the second derivative is just going to be 2. Well, 2 is greater than 0 in this case. So since 2 is greater than 0, that means x equals 3 is the absolute minimum or minimal average cost. All right? So there's a great little insight into that. What I want you guys to give a shot is work on number 25. Give a shot to number 25 on page 228 in your textbooks. Page 228 in your textbooks. Then I'll kind of give you a little shot at trying minimizing average cost. And it is an odd number, so the answers are in your book as well.